Welcome to the video lecture. Today I am going to explain the Swinburns test on DC shunt motor. The main objective of this test is to calculate the no load losses and measure the armature resistance and to determine the efficiency as a generator, as a motor at different load conditions. So this is the aim of this experiment, to predetermine the efficiency of the DC shunt motor by conducting Swinburns test. This is the circuit diagram for the Swinburns test. This is the we are not providing any load, without load, without output, we are not providing any output here, even though we are measuring the both output and input in different load conditions and as a generator, as a motor also. This is the simplest method. In experiment is very simple. Under no load condition, just note down the under apply rated voltage. Just note down the what is the voltage across the armature winding and how much current passing through the field winding and how much current is drawn from the supply. Just note down these three values. Based on that, we are calculating the efficiency of this machine. Suppose it is a worked as a motor, how efficiency is getting in different load conditions, and suppose it is act as a generator, at that how it is getting the efficiency in different load conditions. We analyzed in this test. By using this test data, we are analyzed as a motor, as a generator also. So this is the circuit diagram, you know already. So the main aim of this test is to determine the armature resistance, armature winding resistance simply. So we are connecting a load in series with the armature winding, normal supply. We are giving some voltage. Based on that voltage by current, it gives the resistance of the armature winding. So this is also called as a drop test. The purpose of the test is to find out the armature resistance. So this is the formulas generally. By using no load test, here you can, in the no load test we noted these three values, no load voltage and field current and line current. So here the generally any machine having the three types of losses. One is the electrical losses, second one is the mechanical losses and magnetic losses. So here mechanical loss and magnetic loss are constants. This depends upon the voltage, and remaining the electrical losses, that is called as variable losses, especially your armature winding. Armature winding current, armature current is varied with respect to load. So once the load is varied, armature current is varied. So I square R losses is varied. That's why armature winding resistance losses are treated as variable losses. Remaining losses are called as treated as a constant losses. So here by no load test data, here we find out the no load armature current, total armature current is equal to, so IL naught minus field current. Total line current, no load line current minus field current is given to the armature current. This is very important. So once you know this, just you have to simply calculate the constant losses. Why? Because under no load condition we are not providing any load. That means the output equal to 0. Once the output equal to 0, only, but it shows some IL naught into V, it gives the total loss of the machine. Because you know the efficiency formula, efficiency is nothing but output plus losses is equal to input. But actually here the I want to explain here just for a better understanding. Generally input of any machine is equal to output plus losses. In Swinburns test, Swinburns test is nothing but is a no load test. No load test is nothing but output equal under no load condition. Output equal to 0. So under no load, the total input is equal to only losses. What the losses are available? Generally There are two types of loss. Entire the losses are classified into two types: constant loss and variable loss. One is called as constant loss plus another one is the only I square RA losses. So under no load, I am talking about it is the under no load condition. Under no load, the total input is equal to constant losses plus I square RA. So in this Swinburne test or otherwise the no load test, we are getting these are the values VNL and IL naught and field current. These three values are getting. We observed the circuit diagram. Why here this field winding in series with an ammeter is there, it measures the field current, and here across under initially it is closed. Why? Because this shunt motor starting it takes more current. That's why to overcome that for security purpose or protection purpose, we are providing one switch here. Initially it is closed, but under working condition, under steady state condition, the SPST switch is open. At that time the current is passing through this ammeter. So under no load condition, these ammeter gives the no load current. So no load current. Generally this is the wave circuit diagram, but this is the armature winding, this is the field winding. Once we apply this rated voltage across this, so it draws some current, that is called as IL naught. That IL naught, this is the why? Because this field winding it offers some resistance, that is constant. Here terminal voltage constant, resistance constant, RSH is constant, that is why IF is constant always. And only this one remaining current is IA. This IA is only depends upon the maybe you are providing the load, then only it is varied. So here the some belt drive is provided, we can change it. So IA is this IA is varied with the load. Once the load is changed, always change, but IF is always constant. So IL plus here IL naught is equal to IF plus IA naught. This is the formula in this condition. According to we are apply the KCL here. So from this one we are getting the IA naught is equal to IL naught minus IF. IL naught minus IF. So this is the point we are discussing. So once you, why I am calculated here, by using this test, just we note down these three values. VNL, that is called as, it is measured by VNL. This is called as, it gives the IF value. This gives the IL naught value. So these are the VNL and IF and IL naught. Only this data is noted. So that this experiment is over. Then by applying the rated voltage at the time and under rated speed conditions, we note down these values. Once you noted, and by using this circuit diagram, you find out the armature resistance RA value. So RA value, once you calculate the RA value, then you have to follow these formulas. By using no load, first of all, this no load current, no load armature current is equal to IA naught is equal to IL naught minus IF. So once you calculated this, I told already constant losses. Under no load, the total input is equal to constant losses plus copper losses. Constant losses plus copper losses. So I want to calculate the only constant losses. Here WC is equal to total input minus their variable no load copper loss, variable no load copper loss. So by using Swinburne test data, we are calculating the constant losses only. So this no load test data, it gives the constant losses. Once you know the constant losses, by using this formula, for example, once you calculated the you know the constant losses, then you can calculate the efficiency of this DC machine. First of all, the machine is acted as a generator. This is the formula. For a generator, the efficiency formula is output by input, output by input. So here output is nothing but, we know the formula, output is nothing, generator is nothing but output is electrical, input is a mechanical, input is a mechanical. But you have to mention into once you know the any power, from that one also we are calculating the alike. Why? Because here output is equal to output by input, you can write it like this, output plus losses, output plus losses. So output plus losses. Here output is as a generator, the output values, you know, this is the V and IL. These two values are available in the nameplate details. Actually the machine is working, suppose it gives the, maybe it is the 230 volts rating and the rated current is some 20 amps. So under full load condition, suppose the machine is operated as a generator, under full load condition it delivers the 20 amps. So that's why you want to find out the full load efficiency, we can take it as a, it is a 230 into some IL is nothing but 20. Suppose for example it is the rated 230 volts and 20 amps machine. So like that, here unknown quantity, what is the unknown quantity here? So VIL is known, so V is taken from the nameplate details, IL is taken from the nameplate details. So another constant losses is measured, constant loss is measured from the no load test data, this is the test data. So here the constant loss are measured, and remaining copper loss only, how to calculate this copper loss? So just you know this, under full load condition, for example this is the shunt motor, shunt generator, it delivers the current like this IL, and this is the field current, it delivers the current IA. So IAG, why? Because generator, under generator mode it delivers the current, their input is mechanical, output is electrical, this is the terminal voltage. VT into IL, we are given the total output, but how to calculate the IAG formula? According to this, entering current is equal to leaving currents. So in the generator, IAG is equal to ILG plus IF. So under full load, maybe it is the full load current we are applied, already field current is known, just you can add it, we will get the IAG value. Once you know the IAG value, we can calculate the I square R losses, IAG square RA, we are getting the full load copper loss. That value substituted here, and constant losses is measured from the no load test data, and VL taken the from nameplate details, then easily calculated their efficiency. They are easily calculated as a efficiency. Now this is the formula, input is general input is equal to output plus losses. Under no load condition, there is no output equal to 0, that's why it is act as input is equal to losses, or loss is equal to WC minus WC plus IA square RA. So from this test we can calculate the constant losses is equal to input is nothing but VIL naught minus IA naught square RA. So we are getting the constant losses. For example, you want to know, you want to measure the offload efficiency. How to calculate offload efficiency? What is the variation? You want to generator efficiency, but offload we are calculated. What is the formula generally? For full load, this is the formula, VIL or terminal voltage by output plus losses WC plus IA square RA into 100. For offload efficiency, percentage offload, what the terminal voltage is constant, but only current is varied by 2, you can consider VT into IL by 2 plus it is the loss, constant loss independent from the load, that's why it is not varied. But IA, what is the IA formula? In the DC generator, IA formula IL plus IF, so ILG plus IF, but we want to find out the offload, we take it the by 2. Why? Because IF is constant, only this load current is changed, IL by 2 whole square RA into 100. So this is the formula. But general you want any other load, for example you want to 1/4 load, you take it the 1/4 current of the full load current we are considered, and 1/4 current is considered, here 1/4 current is considered, then you can calculate the 1/4 load. 3/4 load, yes, 3/4 into IL, and we have to multiply it. In different loaded conditions, we generally calculated the efficiency. At any percentage of efficiency of general formula, we can take it the VIL into some x by VIL into some x plus IL into some x plus IF whole square into RA. It gives the efficiency at any case under 1/4 load or 3/4 load, at any load that percentile load we can provide at 0.1%. What is the 0.1% load? What is the efficiency? And so maybe the 3/4 we can calculate at the x place, we can provide at the their value current, load current, and calculated the efficiency. For example, it is as a motor. As a motor, how to calculate it? As a motor, you take this simple shunt motion having field winding and armature winding. We apply the voltage. So we apply the voltage. Why? Because motor input is electrical. It draws the current IL M, and this is called as IF. This is called as a IAM. So according this KCL, total load current is equal to ILM is equal to IF plus IAM. So by using this formula, we can calculate the IAM value. IAM is equal to ILM minus IF. IL minus IF. So thing is, what is the efficiency? Based on the efficiency formula, generally efficiency is equal to output by input 200. But here the in the electrical terminals, by in the experiment we are providing some electrical power, and nameplate details it gives the electrical power formula. Just we can consider in terms of input, we note down the this efficiency formula. Input output is equal to, in terms of input, is equal to input minus total losses of the machine. Input minus total loss of the machine. In the generator, it is the output by output plus losses. In the motor, we can easily in terms of electrical parameter, we can write easily calculated input minus losses by input. The what is the input here? Terminal voltage into load current, VT into ILM minus what is the loss are there? Any machine constant losses, and IAM square RAM, RA or otherwise the motor or generator, the resistance is same, and by VT ILM into 100. So here VT and ILM is considered from the nameplate details. The every machine having their capacity, what is the voltage rating and what is the rated current, or otherwise measured from their HP or otherwise the kilowatts. In terms of watts are given, sometimes HP is given. We converted and calculate the what the their current value. WC is calculated from the no load test, and remaining here how to calculate the IA. Here IA is nothing but by using this formula, IAM is equal to ILM minus IF. So we calculated and substituted here, and RAM is already getting from the drop test, then easily calculated the efficiency. But as like a generator motor also, we can find out the efficiency at any load some X. We can write it like this: VT into load is nothing but off load is nothing but off current, full load means full current. So that it is the fraction now ILM into some X minus here WC constant is why, because it is independent from the load. But what is the IAM value? Simply can write it this like this: ILM into some X minus IF. Yes, it is a yes square RA by VT into ILM into some fraction. What the it is depends upon the load. It is a general formula for the as a motor. The general formula for the efficiency is a motor. So, by using this formula we can easily calculate efficiency at any case of load. So, using usually this is the formula. Yes. So, just for a generator, I just conclude this term how to calculate the efficiency for a generator. This is the formula: output power by output power plus constant loss plus copper losses. This is the generator formula. Like this motor, input minus total losses by input into 100. So, we are giving this 100, and just the observation tabular forms just for a case: no load voltage, no load current and field current, and drop test we are apply based on the circuit diagram. We noted these values, and once you already by using that formulas we can calculate the different loads, and they based on that at full load and full current, armature current is taken at the time, what is the input power, what is the total losses, what is the output power, and finally they find the efficiency. Like that different loads we are calculated. It is as a motor. Like as a generator also same, you can calculate the percentage of efficiency. Once you find out the efficiency, just you have to draw this characteristics output towards their efficiency. So, we observe that compared to the motor efficiencies, generator efficiency a little bit is more. The model calculations also for your benefits I have to given this here. So, no load input VAL naught, and no load armature current, and no load copper losses. Once you find out the no load copper losses, no load input minus no load copper loss, it gives the constant losses. The main purpose of Swinburns test data or no load test data to measure the constant losses. So, the test data gives only constant losses. Once you find out the constant losses, we can calculate the efficiency by using these formulas like as a motor and as a generator. Thank you.